Today is Priya Natarajan, who will give us a review on formation, growth, and feedback of supermassive black holes. Thank you.
OK, good morning. Thank you so much for turning up early. So what I want to do today, first I want to say thanks for inviting me to Heidelberg. It's my first visit, and it's absolutely beautiful. It's a wonderful place. So what I want to do is to give you a status report and an overview of our current understanding of the formation, accretion physics, and the growth history of black holes in the universe, supermassive black holes. Of course, the focus is on trying to understand what the initial seed masses need to be in order to produce what we see over redshift observationally. So at the moment, as you all know, we don't have any direct observational evidence for the first black holes. And so part of what I'm going to do in my talk is to talk a little bit about the several channels for making the first black holes, and hopefully make a persuasive case for the direct collapse black hole scenario. And partly, what I have been interested in, and a lot of modelers since have been interested in, is sort of the cosmological context of black hole growth. So with our growing understanding of galaxy formation and the properties and potential co-evolution of the properties of the galactic hosts that host black holes and the black hole masses, as well as the impact that black holes have on their environment, it looks like we need a comprehensive model that fits into the cosmological context. We can no longer just do sort of individual. I mean, we learn a lot by looking at individual simulations which are not cosmologically patched on. And we also learn quite a lot by looking at large cosmological boxes where we can't resolve a lot of the physics on small scales. So the idea, of course, is to somehow synthesize and making sure that we keep the key elements of the physics in there. So what I want to show you is how the observational, given the lack of observational evidence at the moment for direct collapse black holes, or any first class of black holes, say population 3 remnant black holes as well, that since they have to fit into the larger structure formation picture, we have observational constraints at low redshift, starting locally all the way up to 6 and 7 now, for both dormant black holes and accreting black holes. And so any model that we have, any physical model for the formation of the first black holes, has to tie in. And we are looking for observational signatures at extremely high redshifts, but they also have to tie in with what we already see of growing black holes. So we have many, many constraints on the late evolution. So what I want to give you a feel today for what the constraints are for the early evolution, and what stages might actually be observationally accessible. In particular, what's really exciting, as I'll end the talk showing you, that JWST might be just the instrument that we need to actually discriminate seeding models. Part of the problem is that once material has crossed the innermost stable circular orbit in a black hole and accreted, as it were, there's no memory of the initial conditions of how the black hole actually assembled. So that's partly the problem. So what we're going to hinge on is the properties of the environment in which the first black holes form, the environment in which they are embedded, the feedback and the impact that these black holes have, and what observational signatures we can actually glean from that. So first, before I move, this subject has been going through a real rapid growth in the last 10 years or so. So I should apologize. This is a partial, but this is a list of people, a lot of them younger people, who have been actively working in this field for the last 10 years or so, many of whom are in the audience today. So it's a particular delight to have the option to speak when so many of you are here. OK, so one of the key challenges in understanding and modeling the impact and the formation of black holes is the challenge in terms of, there's a physical challenge, and I'll show you later, there's a timing challenge. So this physical challenge is what limits us computationally from just going ahead and starting from a cosmological box with cosmological initial conditions for the model for Lambda Cdm, which we know is extremely successful, and then zoom in and start making ab initio black holes, following their growth, and so on. So just to give you a flavor for how punitive the scales are, the scales that you have to combine are, that if you look at the black hole at the center of the Milky Way, the Schwarzschild radius is about 10 to the 12 centimeters or so, whereas the cosmological scales, the scales from which the gas is fed onto the black hole, of course, the one in the Milky Way is dormant and it's not being fed, but the scale that we're talking about is 10 to the 26 centimeters. So having one calculation, a computational simulation in which you can resolve all these scales has been very, very challenging. And so the approach that most of us have adopted is there are people like me who are looking at the physics and trying to boil down what is the essential physics that we need to be able to model appropriately. And then there have been people who've been following a numerical approach and trying to cascade the scales. So some very high resolution simulations with small boxes, with finely tuned sets of initial conditions, two large cosmological boxes in which you have you make only initial assumptions about initial conditions for the cold dark matter, relevant to cold dark matter. So, and in these pictures, so first let me show you what are the constraints for these models downstream, from low redshift to high redshift. So observational constraints that all our models have to satisfy. So the first is we now have many secure multi-wavelength observations for both active and quiescent black holes. And what we find, by and large, that there's a real distribution in the masses of black holes. But roughly in the centers of galaxies, they range from about 10 to the 6 to 10 to the 9 solar masses. And we've occasionally found very ultramassive black holes as well in the nearby universe, as well as at very high redshift, about 10 to the 10 solar masses. And we have observational detections from a redshift 0 to 7. And so we have individual cases that we have seen, so individual AGN, high-resolution studies from Hubble Space Telescope, Chandra, Spitzer data. And then we also have the integrated contribution of growing black holes provided in terms of the cosmic X-ray background, cosmic infrared background, and so on and so forth. So what I want to point out in particular is that one of the key challenges that's going to come up, as I alluded to earlier, is the timing challenge. So we are starting to see accreting black holes as quasars at redshift 7 and above when the age of the universe is about 660 megayears. So it's only about 500 to 600 megayears after the Big Bang. So it's a huge challenge to figure out how you can assemble 10 to the 9-ish solar masses by these very, very early times. And so the other thing we do know is that growing black holes do affect and impact their environment. And so there's evidence on both galaxy scales as well as black holes in the centers of brightest cluster galaxies and clusters. So this is just to give you an overview of the current senses of growing black holes. So this is a plot from Benny, Trachtenbort, which shows you what the masses are, the estimated masses for observed black holes at the moment as a function of redshift. And notice that we have several candidates that are above 10 to the 10 solar masses. In particular, I want you to look at redshift 5 and above and to see that we are increasingly starting to find several candidates that lurk around the 10 to the 9, above 10 to the 9, 10 to the 10 solar masses. And these are the ones for which we have the acute timing challenge that I talked about. So in terms of understanding, as I said, the large-scale understanding from sort of the cosmological context, what we now know is that at very high redshift, the merger rate in Lambda Cdm is quite high, and therefore we can anticipate, as long as black holes are seeded fairly frequently in the early universe in collapsed halos, that they would grow both by gas accretion as well as mergers. And the question is, what is the balance of growth that is accretion-driven, gas accretion-driven versus actual mergers? And it turns out that we had a very simple picture about 7-8 years ago, where mergers were thought to be everything. So mergers were believed to trigger accretion episodes, and the whole framework was driven in a sort of a merger-driven approach. So, but what we found upon more careful modeling as well as trying to match with data, as I'll just show you some challenging data sets, have forced us to understand that you need growth, combination of mergers as well as accretion-triggered mergers, as well as a quiescent, long-lived, steady trickle. Okay, so you need all these 3 different accretion modes. And this is going to be of interest because this gives you the level, gives you a feel for the kinds of accretion physics that we may have to play with, the uncertainties that we have in understanding the formation of the very first black holes. But what we do know is most likely the brightest quasars in the universe are triggered. Their activity is triggered during gas-rich mergers. But if you look at the massive black hole that's sitting at the center of a brightest cluster galaxy, then the growth of that black hole from redshifts of about 2 to 0 have occurred not through gas-rich mergers, because these are gas-depleted environments at these redshifts. And so that growth of about 10 to 20% of the final accumulation of mass for the most massive local black holes, low redshift black holes, has happened via direct mergers. Whereas at very high redshift, the mergers of halos and gas delivered through those mergers, therefore accretion that is triggered by mergers, appears to be the dominant growth mechanism. So there's a real dichotomy in terms of the masses of black holes, the redshifts at which you are measuring these masses, and therefore what the growth histories could have been. So as you all know, I'll quickly go through this. So in terms of observational constraints, there are a whole bunch of correlations that are seen. And it was believed early on that the correlations were extremely tight. Of course, we knew that there were probably systematic biases and observational biases. What we now know is that in these correlations for black hole mass, central velocity dispersion of the bulge for the host, there's a lot of dispersion, and there are actually many outliers. And in fact, there's a lot of information in the outliers, and we are just starting to detect these outliers in these relationships. So what's very interesting is local demography is showing us that you can have very, very massive black holes. So if you look at the left-hand plot, you notice that the highest mass black holes, and the y-axis is black hole mass, or again, there's a huge number, about 10 to the 9, 10 to the 10 solar masses. And these are the ones that are the centers of clusters. OK, so the other correlation that we do know is that the black hole accretion rate. And so when we talk about the black hole accretion rate, in the context of sort of thin disk accretion, we're really talking about the mass inflow rate across the innermost, across the ISCO. So that's really what we're talking about when we say the black hole accretion rate. And then we have accretion models that we use to translate that m dot into luminosity, and then we catch up with observations. So there's a couple of steps, and I'll just talk to you about what the uncertainties are in terms of our understanding of the accretion physics in just a moment. So we already see that there are correlations between the integrated the star formation rate, star formation rate density, as well as the black hole accretion rate as a function of cosmic time. So notice, of course, the energy density that is outputted by accreting black holes is actually several orders of magnitude lower than that that's coming out of stars. It's just artificially scaled on this plot to show you that they track each other. So one of the most interesting data sets that really torqued all our models, leading us back to questioning our assumptions about seeds, was this data set from SDSS by Brandon Kelly and collaborators. So this is a census of the most massive black holes between redshifts of 1.5 to 4.5. This is the bulk of where the action in the universe happens. A lot of the star formation is happening at these epochs. And so we had, from broad-line quasars in the Sloan Digital Sky Survey, so we had a good idea of the mass function as a function of redshift slices for the most massive black holes. So now the goal of the models that I'm going to show you is to reproduce all this data that I have. And in particular, it turns out that this is a very interesting and important stringent test. OK, so what is the timing challenge? The challenge is, as I mentioned, that by redshifts of 6 and 7, when the universe is quite young, you already have very, very massive, supermassive black holes in place. And the question is, what is the combination of initial conditions in terms of the initial seed masses and the accretion physics that would allow you to get this kind of? And as you all know, in Lambda Cdm, given the statistical nature of the theory, if you found 1 or 2 freak objects, they can be accommodated. But the problem arises when you have a population. And so we are seeing hints of populations of black holes with very high masses already in place. And so that has prompted us. So this is just to give you a sense of what this timing challenge actually means. So suppose you want to end up with a final black hole mass of a few times 10 to the 9 solar masses. If you want to end up at redshift 7, so you're observing a bright quasar that appears to be powered by accretion onto a billion solar mass black hole at that redshift, then with Eddington limited accretion, so if you believe the Shakura-Sunyaev model, sort of a thin disk accretion with reasonable radiative efficiencies, then you expect the seed, you need a seed that is about 10 to the 6 solar masses to comfortably give you that by redshift 7. Of course, if you are seeing these very massive black holes at lower and lower redshifts, then the constraints are less stringent. So you could start with a lot less massive, very light seeds, and you could still work it out. Say, for example, if you look at the redshift 3 brown curve, you see that you could start out with much lower masses and still end up with a 10 to the 9 solar mass black hole. So this is really sort of the key timing challenge. And so what this suggests automatically is that, if you start off, obviously, with more massive initial seeds, so this is sort of the final, closing word, really, on what's going on with the initial seeds, black hole seeds. So this is a synopsis of everything. So if you zone out after this slide, it's fine, because this is the slide that you need to stay awake for. So the key challenge from the previous plot, you saw that you basically need 10 to the 6 solar masses assembled in black holes by, say, redshift 10 to 15, depending on how far the window is where we are detecting the most distant quasar that pushes out that window. So basically, you need 10 to the 6 solar mass black hole by redshift, say, 12. And there are many ways to get there, right? So the play that you have is that you could start with lower seed masses, so you could have population 3 remnants, and then you could invoke accretion physics. You can invoke super Eddington growth rates, and then you can bring them out to about 10 to the 6, 10 to the 4, 10 to the 6 solar masses. And so the other interesting suggestion that many of us have been working on for a decade and working out is what happens if you start with initially very high seeds, high mass seeds, so 10 to the 4, 10 to the 6, from the get-go. So you assemble very, very high mass seeds right away, rather than starting with a light seed, which is a population 3 remnant, and then amplifying its growth by a whole bunch of different channels, right? So the goal is ultimately, the ultimate constraint is to end up with a 10 to the 6-ish solar mass black hole by redshift 10 to 12, right? So of course, there are many sort of big questions when we are trying to build sort of this integrated picture of the accretion history, starting from some initial seed masses down to what we see at redshift 0. So what I'm going to do now is give you a very quick overview of our current understanding of how we would grow these black holes from a bunch of different initial seeding models, which can be broadly classified as light seeds and massive seeds. And from now on, the light seed model that I'll be talking about is one which involves population 3 remnants. And the massive seed model will now be synonymous with the scenario that I'm going to call the direct collapse scenario. And so if you look at the number of ways in which you could start with light or more massive seeds, you find that the uncertainties in each of these channels, so you might have seen all the talks in the conference earlier, which talked about the uncertainties in the population 3 scenario. So the challenge in what the actual mass function of those initial black holes, of the initial stars is, which then translates into a mass function for what you would have for the black hole seeds. So, and one of the interesting things is the timing challenge. So we need to keep the timing challenge keep that in mind. And any scenario that involves POP3 necessarily requires periods of super Eddington accretion. So just as mergers were solving every problem in galaxy formation, black hole formation 10 years ago, now the fact that in certain GR-MHD simulations we are able to find super Eddington flows, everyone's throwing up their hands and saying, well, we don't need any massive seeds because you can just start with very light seeds, and all we need is super Eddington accretion. So there's some really important physical constraints with super Eddington accretion that we don't understand quite as well. And that has to do with the radiative efficiency of those flows, the geometry of those flows, and how those geometries actually transit. So what we find is that sustaining a super Eddington accretion for very long periods of time is extremely difficult. And you would need so you could have small periods of super Eddington accretion, and then you would have to somehow alter the geometry and move away from sort of what we call slim disk accretion to thin disk accretion. So all these transitions are not as well understood at the moment. So I'm just trying to do a hard sell for the fact that we really need to think about more massive seeds and direct collapse black holes. So what is very, very interesting about the direct collapse scenario is that the conditions that are required to effect and to have a runaway collapse into a massive black hole seed are available in the early universe, right? And that's what many of us have been working on over the past few years. So to start with, the broad brush thing that you need is you need metal-free gas because you need to prevent molecular hydrogen cooling and fragmentation. So essentially, you need a halo very early in the universe, which is gas-rich, which is essentially primordial, dominated by atomic hydrogen cooling, that somehow forms some kind of proto-galactic disk that goes unstable and doesn't actually fragment, but actually pushes with bars and bars or some non-axisymmetric structures, pushes a lot of matter in and angular momentum out. And so those sort of models have been worked out, and I'll just show you how they refine our understanding. So this is just a tabulation to show you the various mass ranges for seeds that you can get from the various scenarios. So as I said, I'll be focusing mostly on the implications of the direct collapse scenario downstream and how we can actually distinguish that. So I want to make a quick note of primordial black holes. And this is something that is really not talked about much, and actually with very good reason. There are very few constraints. So there are these models where very early in inflation, when you have a first order phase transition, you could possibly form a whole bunch of very, very tiny, but there's no constraints on the number of black holes that you could actually form in these kinds of models. And the only constraints we have are way downstream when we are looking at, say, redshifts of 10-ish. So we have the integrated background radiation, the infrared background, as well as the X-ray background. And so we find that now with better measurements, there's an unresolved excess. So if we that's the only constraint we have on the primordial population. It turns out it's not particularly stringent at all for the primordial black holes. And in fact, all the unresolved excess that we find now can be explained with either direct collapse black holes that form by redshifts of 20-ish, 20 to 15 down, or even POP3 black holes. So this is the reason you don't hear so much about the primordial black holes. It's a very poorly constrained scenario at the moment. So in terms of, so you may ask, why do we really need massive seeds? Do we need them? So it turns out that the wonderful simulations done by many people in this room for formation of population 3 and looking at the remnants find that there's actually very little growth onto the sink particles, which is how the black hole remnants are modeled from. So the black holes in these simulations simply don't grow very much down to redshifts of 8. And remember, by redshift of 8 is when we want the bulk of the growth. We want these to have really reached 10 to the 9 solar masses or so. And what we do have now, of course, in Lambda Cdm, the other thing that you have available to you is that you could always move up. You can make more rare objects, so you can go on to higher significance peaks in the dark matter distribution. So you can go now to, say, the 3 sigma peaks rather than 2.5, or 3.5 sigma peaks, and see whether in those circumstances you could have a few seeds that are retained in halos where they can grow very rapidly. So it turns out that you can arrange that if you go to higher significance peaks. Then the trade-off is that they are rarer, right? So you have fewer. So given our growing understanding of the number of high redshift bright luminous quasars at redshifts greater than 6, we don't have the faint end of that luminosity function is not sampled yet. We are seeing the brightest guy, so we don't have a good handle on the overall abundance. So if we have constraints on the overall abundance, that will limit how far in terms of the peak significance we can actually go to. So this is some very nice work on POP3, which is we have a slightly better understanding now of the initial mass functions and therefore of the remnant masses. So this is some little work that we did a few years ago, starting out with light seeds. Remember, I said the challenge is you can start with light seeds or with massive seeds, but you just have to grow them to about 1 million times the mass of the sun by redshift 15 or so. So one thing you could do is you can come up with these interesting dynamical scenarios like we did. So for example, if a seed black hole of, say, a few solar masses, 10 solar masses, no longer defines the potential, is not the, does not define the potential, is not sitting in the center, and it's actually bouncing around and doing a random walk in a dense nuclear star cluster, which is very gas-rich, then it can actually grow and grow to about 10 to the 6. So there are light models that can grow to make the kinds of seed masses that we want. So let me now focus a little bit on the direct collapse scenario, where the idea is very, very simple for those of you who haven't seen it before. So you have baryons inside a collapsed dark matter halo that form a pregalactic disk. This is an unenriched atomic cooling halo. And the disk becomes gravitationally unstable and starts to rapidly accrete to the center rather than fragment. So there are regimes where the ratio, for particular values of the ratio of the gas temperature to the virial temperature, you can actually have regimes where you have no fragmentation and actually accretion to the center. There are regimes where you would have both fragmentation to stars as well as growing black holes, and so on. So here we focus on the case where you're just basically funneling a lot of mass and you're forming direct collapse black holes. And so the interesting thing about, so now we are slowly starting to investigate them in simulations, this process, to see whether you could make these very pre-galactic disks, unenriched disks, and the fate of these disks, and whether they indeed go unstable as we expect analytically. So there's been a lot of progress. So the interesting thing that we find is that in order to actually to form direct collapse black holes, you need to have an external source of radiation that pumps out Lyman-Werner photons that will actually dissociate any molecular hydrogen that is forming, that will then prevent fragmentation. So the whole idea is to prevent fragmentation. And what that implies are very specific environments where this is possible. So you need a prior stellar population, a population 3 halo, and a direct collapse halo would be a satellite. So this is how our understanding has been refined. We now know spatially what are the kinds of regions where you could have efficient direct collapse. So of course, the fate of, it's very easy to say that you just funnel the gas to the center. The question is, what is the fate of the gas and what is the precise structure? And what we find is this, this is a part that is a little uncertain. There's a lot of work at the moment on this, which is you have the structure which looks like a star, which is a supermassive star, and it looks rather like a bloated red giant, and you have accretion from an envelope onto an initial seed that has collapsed, and then you can end up again with a 10 to the 5, 10 to the 6 solar mass. So as I said, a lot of the work that I have been personally involved in and my research group has been trying to embed all of this into the larger framework for structure formation. So in the context of the Lambda Cdm model, where growth is driven by the merger hierarchy of dark matter halos. So when you do that, you can start out with these initial seed models, either POP3 or massive seeds, and that's a mass function at a redshift of 15. Notice that for direct collapse black holes, the peak is roughly 10 to the 5 solar masses. That's the typical mass of, so the highest mass of the seed that you could form. And then this is the sequence of what we do. So you start out with a seed, and then you grow it in the context of merging dark matter halos. And there you again have a choice of the growth mode. So you can either talk about growing them in an Eddington-limited fashion, which has implications for the particular geometry, or you can invoke super-Eddington accretion or sub-Eddington accretion. So there's a lot of play here in terms of the models. And the idea is, ultimately you have to end up at redshift 0 by redshift 0 on the M-sigma relation that we know. So in terms of the possibilities for accretion physics, there are largely speaking, there are two key ways in which you could actually grow them depending on the geometry of the flow and the environment. The first is the steady standard Eddington-limited accretion, where you have a thin disk, and there the luminosity that comes out is just proportional to m dot, which is the mass inflow rate. Or you could have these radiatively inefficient flows, the so-called slim disk solutions, where the luminosity that's coming out is proportional to the log of m dot. So you can see already that these are two fundamentally different physical scenarios for growth that have implications in terms of time scale. So this is very nice work done by Kwang-Ho Park and Massimo Riccati, where they've been looking at the accretion physics. And broadly speaking, there are two modes. So you have a feedback-limited mode, where you have very inefficient growth. And you could have outflow, so you could actually lose some mass, as well as have mass inflow. And in those scenarios, only 15% or so of the gas reservoir that's actually available, so independent of the cosmic context, only a small fraction of it makes it down to the hole and gets accreted. And so typically, they find that for low mass seeds, you're mostly in that domain, in that regime, right? So this is one of the reasons why if you start out with very low mass seeds, light seeds, it's actually very hard to grow them very, very rapidly, unless you have intermittent super Eddington modes. And then the question is, how do you change the geometry from one to the other? What is the time scale for the change, and so on? So the other mode that they find in terms of the accretion physics is a gas supply limited mode, where essentially it's super Eddington growth, and the outflows are no longer important, and the inflow rates are extremely high. But the radiative efficiency is very, very low. But about 80% of your gas reservoir can be very, very rapidly accreted. So this is the hyper growth mode for the black hole itself. But this growth mode could be quite obscured. And this is very interesting because population synthesis models of the X-ray background suggest that there is room, given our current data, for a huge obscured population. So the question is, no matter what seed you start out with, whether they're growing in an obscured mode or they're growing in a mode that you would see as bright luminous quasars, right? So this is one of the key other sort of uncertainties in the problem. But what we find, and they report, and they've done sort of more detailed studies over the years, is that most massive seeds that are embedded in gas-rich reservoirs tend to be in the gas supply limited regime. So this is just to show you some individual accretion histories for black holes. So how you would assemble in the framework of these Monte Carlo merger trees the final masses of 10 to the 9 solar masses. So let me quickly move on to show you a quick animation of what we do now. So with a combination of several physics possibilities as well as initial conditions, we can start populating the M-sigma relation. And so depending on the seed models, you actually get very, very different predictions for the scatter, and that is because of the growth. So when you have massive seeds, you actually have a stage, very early stage, where the black hole dominates, the mass of the black hole dominates the inner regions, and unlike the low redshift M sigma, you see the converse. You see that the stellar population is subdominant compared to the black hole. And that stage is called the obese black hole galaxy. And that's a very interesting discriminating point between light and more massive seeds. So I just have final 2 slides to show you some new results on how you could actually discriminate seed models from just looking at this transient stage. So there's a transient stage where the massive black hole seeds will be in a halo where they dominate, their mass dominates compared to the stellar component that they have acquired by merger, whereas light seeds, the black hole mass is subdominant compared to the mass of the stars. So you can actually, we've computed recently with Fabio Pacucci comprehensive spectral SEDs over multi-wavelength SEDs. And so this is, I'll just stop with this one. So this is our prediction with JWST. And you can actually see there are many templates here of potential confounding sources. And you can actually see that you could easily distinguish the direct collapse black hole scenario from POP3 remnants if you focus on between 1 and 10 microns and you look at the slope. So I think the prospects are very, very bright. I'll slip over these because these are going to be talks that people are going to give you more details on many aspects that I've just highlighted here. So there are many, many open questions, but I think JWST offers great potential in discriminating not just the initial seed scenarios, which are otherwise inaccessible, but also it has a great prospect in providing new constraints to add on to the other multi-wavelength constraints that we've had over the years. Thank you so much. Sorry. Have I eaten into my question time a lot?
Somewhat. I mean, it's down here, the counter. So.
Yeah.
OK, questions? Volker. And all of you next.
So what are the prospects if LISA flies in further constraining this whole question that you have mentioned?
Well, I think obviously the clinching thing for with Lisa will be the fact that we have a merger-driven scenario very early on in the universe, and we have expected event rates that we can predict as a function of redshift. So even finding a handful of events would really calibrate those models. And we may have to rethink if it turns out that the mergers are not as frequent or they are more frequent. I think that could be very important constraints, additional constraints. It's just that I was talking about constraints within the next 10 years. So.
Yes. Hi, Priya.
Hey.
Thanks for your talk. I just wanted to comment on the statement you made about that the possibility of primordial black hole is very unconstrained right now. Actually, there are some pretty strong constraints that come from their effect on the cosmic microwave background radiation. So one can argue, depending on the mass.
I was going to say the biggest uncertainty is the initial mass that you have for the primordial black hole. Of course, there are certain masses, 10 to the 6 solar masses, 10 to the 4 solar masses. That's right. There's a very nice paper by you where you talk about the various. But if you look at the formation at inflation, those masses are really quite uncertain. What those masses are, very highly unconstrained. So very low masses are, wouldn't you say that masses below 10 to the 4, there really aren't very many constraints, 10 to the 4 solar masses?
Yeah, you can have a lot in order to explain intermediate mass black holes, perhaps, or ULXs, let's say, or seed black holes from supermassive black hole, but they, at least from those results, they can be a pretty small fraction of the dark matter.
Right.
So
they can
1
be
part in 10 to the 5, let's say. So they're constrained quite a bit, up to tens of solar masses.
Right, and I mean, there's also this new idea that Simeon Bird, Kamienkovsky, and others have come up with, where about 5 to 10% of all dark matter could have been primordial black holes that are primordial in the sense they produce very early, not necessarily from inflation. But that's because there's a small window under 100 solar masses that is still available after Macho results, right? That you could play with.
Yeah, they mentioned my paper in their paper, and they say, okay, there is this paper that says they cannot be, but there are big uncertainties, so we just ignore it and go on. Right. But thanks.
Mike Norman.
The direct collapse black hole scenario seems to require a luminous neighbor galaxy to photodissociate the H2.
Yep.
So wouldn't that predict that there would be a galaxy near every one of these high redshift supermassive black holes?
Yep.
What's the possibility of looking for them?
You mean looking for the particular combination of having a high redshift galaxy and a location where you have a DCBH?
Right.
Yeah, obviously. But I think at the moment, given how rare direct collapse black holes are, it's easier to look further downstream when these direct collapse black holes have formed and they are in that transitory stage, the obese black hole galaxies. And I think Bhaskar Agarwal has done some very nice work showing that given the rarity of these halos where you can affect direct collapse black holes, that it's probably more efficient to search for that stage rather than the combination. Ultimately, of course, it would be wonderful to even test that and to have the...
But we can see luminous redshift 7 galaxies.
Barely.
With the Hubble Space Telescope, we have bushels of them. So, I mean, what about simply looking at the high redshift quasar, looking in the vicinity and seeing if there is...
That's right. So, I mean, there are current studies... So you'd need the Chandra deep field. So these direct collapse black holes, as soon as they're formed, because there's a paucity of a stellar component, they would be most easily detectable in the X-ray. So there are these sort of cross-correlation studies, but we don't have deep enough Chandra images, even with the deepest images that we currently have, to find those combinations.
Thank you.
Maybe one last question, if the question is brief and the answer is also very brief.
Okay, I'll keep it brief.
This for CR7 and the X-ray output, we'd have to have a year of Chandra exposure time, so we won't see them directly in the X-rays.
We won't see them directly, yeah.
The other challenge is that the galaxy doesn't have to be as bright as you think because of H- photodetachment.
Fair enough. Yeah.
Okay, Chiaki, you had also one.
So demonstrate the time evolution of M sigma relation in two different cases. But you don't expect any points become above the relation at some point, or?
No, you do. So there's a transient stage. This is for obese black hole galaxies. For high mass seeds, direct collapse seeds at very high redshifts, you will be overmassive compared to the local M sigma relation. Absolutely.
And okay, one last question.
Thanks. I do have a small comment which might make the direct collapse scenario a bit more difficult, and that's when the Lyman-Werner radiation from the neighboring galaxy is actually not able to get out of this galaxy, but instead is being trapped by the halo. And
fair enough. Fair enough. This is assuming that that there is a finite escape fraction. I think the various talks in this morning will be talking a lot more detailed about the caveats, the difficulties, and the possibilities for this. Okay. Thank you very much for your attention.